So we have our three postulates of quantum mechanics: that everything is described by an element of a Hilbert space, that those elements evolve linearly according to the Hamiltonian and Schrödinger's equation, and that if we measure them, they stop evolving linearly and they suddenly jump according to the measurement postulate. Now, these three postulates have consequences. We first discussed the fact that if we have linear evolution, then we can describe the evolution just by a single operator. That operator turned out to be unitary, which is that its inverse is its own Hermitian conjugate. And then we discussed the fact that if you have all your evolution in terms of that evolution operator, then you can naturally group it either with the states or with the operators or with both. We then looked at transformations, which are families of unitary matrices. And we discussed that Noether's theorem showed that if the Hamiltonian commuted with that transformation, then the generator of that transformation was conserved, and so you have a conserved physical quantity. The generators are always Hermitian operators and therefore can be observables. We discussed that momentum was the generator of translations, and we discussed that angular momentum was the generator of rotations. Those can be thought of as the definitions of momentum and angular momentum. And then we realized that we've been talking about momentum as three operators and angular momentum as three operators. And in fact, there's this idea of a vector operator. And this usage of the word vector is different to the usage of the word vector that we've been using up here. So if you're living in a vector space, and of course every state is described by a vector, it's a state vector. But this is the older fashioned version of vector, or kind of a blended one, where we're talking about vectors in three space. And so in three space, a vector operator is a set of three operators whose components transform just like vectors do. And our strict definition is that we're going to say a vector operator transforms as vectors do under rotations, just to make it very explicit. So in quantum mechanics, a rotation is described by a unitary operator, which in turn has parameters of a vector, and we're going to break that vector into a unit vector and the amplitude of it, which is an angle. So this is a unit vector. And I'm going to write unit vector there rather than put a hat on it, because that will enable me to distinguish between unit vectors and operators. Now, because rotations around a given axis are additive, then this is just described by an exponential. The angle times the generator, and the generator is that unit vector dotted with this triplet of operators, and this is the generator for the rotation around this given axis, and this triplet of operators enables us to get the generator for rotation around an arbitrary axis. So this is the angular momentum, which is a vector operator. So in quantum mechanics, a vector operator is a set of operators that transform like a three vector transforms under rotations. What do rotations look like? Rotations for three vectors are just 3x3 matrices. So if I have an initial vector with Cartesian coordinates x, y, and z, then I can describe my rotation just by a 3x3 matrix, and then I would get my rotated version. The exact form of this is a little bit complicated if you have a completely arbitrary rotation around an arbitrary angle, but say for rotation around the z-axis, obviously I'm not going to change my z-axis, and I know my rotation in 2D. And if instead I rotate around the other cardinal axes, then all I do really is rearrange these rows and columns. I get cos minus sine, sine, cos across the ones that I'm not rotating around. And in between, of course, I do get a more distributed version. Mathematica, by the way, can calculate this matrix. If you plug this into Mathematica and use a command called rotation matrix, then you can calculate this for an arbitrary axis and arbitrary angle very easily. But although the general version is complicated, we can get a very simple algebraic form if we just consider a very, very small rotation. So in the limit that theta is very small, of course, we don't get coses and sines, we just get ones and thetas there. And in fact, it's very easy to convince yourself that if you want to rotate a vector a small amount, you start with the original vector, and you're going to add a little bit. And you're going to add a little bit at right angles to this vector, and it's also going to be right angles to our rotation axis. And we know a vector that's right angles to both of those. It's the cross product of the two. And indeed, you can get the sign right just by using the cross product like that. Now, the cross product is well known to all of us, and it's also a very compact version of this equation, but I want to break it down into components instead of leaving it there. And the reason I'm doing that is twofold. The first reason is that we're about to do a bunch of algebra on this equation, and rather than remembering a large number of vector identities, I'd like to just use normal algebra. And the second is that later on in the course, we're going to be going on and doing more generalized versions of vectors and tensors and so forth. And the notation that we're going to start to bring in here is going to be very useful there. So the ith component of this vector here is going to be equal to the ith component of this vector. Nothing strange there. Plus the ith component of this cross product. And the ith component of this cross product can be written as sum over j and k, sum tensor rjk nj rk. Now this tensor here is called the Levi-Civita or antisymmetric tensor. And it is very simple to define. It's 1 if rjk is an even permutation of 1, 2, and 3. It's -1 if they're an odd permutation of 1, 2, and 3. And all the other components are 0. So if any of these two indices are repeated, so epsilon of 1, 2, 2 is 0 because it's not either an even or an odd permutation of 1, 2, 3. Okay, another thing I'm going to introduce here is that when we get and use these kinds of tensors and this tensor notation a lot in special relativity, we can get really bored writing down all these summation signs. But actually these summation signs have to be there. Why do they have to be there? Let's look over here. This thing here depends on I. So this thing here, whatever it is, it's only allowed to depend on I. And this one's got j's and k's, so they must be summed over. So we kind of assume that that is there even though we don't write it. So without that there, we still imagine that in fact that summation is there. And this is called Einstein summation notation. So we can use Einstein summation notation to write the new coordinates in terms of the old coordinates. It's just a matrix multiplication. So matrix multiplication, there's my new coordinates. It's just a matrix multiplied by my old coordinates. And this matrix here is a function of the angle and the vector. And we can see what that is from here. So this is just the diagonal part. So we have a delta function. And this bit here is more complicated. So this thing here, because we've got an implicit sum over j there, this thing is a function of ik, so we've got an implicit sum over k, and that gives us our new coordinates. So now we know the form of the rotation matrix in terms of the angular momentum, and we know the form of a rotation for at least infinitesimal rotations, and so we can put those together. Remember, the definition of a vector operator is some set of operators whose components transform as vectors under rotations. How can we formalize that? So what we've done here is we demanded that any inner product between arbitrary states of a rotated operator AI, if it's a vector operator, it has to look just like the rotated version of the inner product as if it was a classical vector, just a 3 vector. And in fact, because that's true for arbitrary phi and psi, arbitrary states, we can show that that relationship is also true for the operators directly. And we know how to expand this for small angles because we just get the generators, and we know how to expand this matrix for small angles, so we can go ahead right now and do that. Well, you'll note that because we use j as our dummy index up here and we've kept it down here, that we've effectively, compared to this formula, reversed the usage of j's and k's. That's completely fine, because remember, j's and k's are dummy variables, and we can call them whatever we like. We could turn k into something else, j into k, and then that something else back into j, and so we can swap them happily around. And I'm leaving it that way because I really want to hammer into your minds that dummy variables can be chosen arbitrarily. Now, the 0th order of this is simply that ai equals ai, so that's simple. Let's have a look at the first order. Where you'll see I've expanded out the dot product into its components and using the summation over m and the summation over m on the other term as well. And I've deliberately used different dummy variables over here as over here so I don't get confused. So this is clearly a function of I, and this is clearly only a function of I. Okay, now this is true for all choices of these unit vectors n. So this is true for all n. And therefore we can pick them in order to select out particular quantities of these, which means we can show that. And so this relationship here, the commutators of any vector operator have this relationship with the generators of rotations, which is angular momentum. That's true for all vector operators. And to do this, we had to swap the order of two of these indices here, which gave us a minus sign.